Hello, happy Monday or Tuesday, whenever day you're watching this. We are on lesson 17, very close to ending this quadratics unit. Don't mind what it says for homework or do Monday. That's obviously if we were in school and on a regular track here. But our aim today is you'll be able to graph and interpret quadratic equations. So we're kind of looking like real world problems. We've seen some real world problems before. We've talked about them, but we're just going to go in more depth, be able to look at the graph, using the calculator, using GeoGebra, evaluating the points, evaluating the domain and range type of thing, right? So we're digging more into this, just so we really know what a quadratic is and what information it can tell us based on a real world situation. So we'll go over the notes and I'll show you what how to use GeoGebra with this lesson. And you can also use your graphing calculator, and I'll tell you how to get some of the stuff using it. I won't be able to view the graphing calculator, but I'll be able to write down and tell you. But I will be showing on GeoGebra, so if you want to do it along with me, you can open up a tab and use GeoGebra for this stuff, or you can just watch me as I go and figure GeoGebra out as we go. And then so you'll take notes on this stuff, and you don't have to write out the problems. You can just write out do now. You can write out problem 1 with the questions if you want, and then there'll be one long problem for you to do independently with what I've showed you here. Okay, and this is due Tuesday night by midnight. Hopefully you're all caught up. If you aren't, please make sure you're handing in missing work. The first 5 lessons I assigned as a resubmission, so please do those if you didn't do lessons 1 through 5, not 1 through 5, whatever we started with. I don't remember the lesson number right now. And if you do need help, we can schedule a Zoom if you want, because I have some students already that want to do extra help from both courses. Okay. All right. So looking at the first one, a high school baseball player throws a ball straight up into the air. I don't know why my music just started. Oh, my Apple Watch. I don't even know what happened. My bad. All right. A high school baseball player throws a ball straight up into the air for his math class. The math class was able to determine that the relationship between the height of the ball and the time since it was thrown could be modeled by the function h of t equals negative 16 t squared plus 96t plus 6, where t represents the time in seconds since the ball was thrown and h the height in feet of the ball above the ground. So they asked us what's the domain, meaning what does x represent in this function, and x is considered t. Remember, f of x or h of t is the same thing, so this is talking about time. So if we input time, we can figure out the height of this ball that's in the air, on the ground, whatever happens. It's in seconds since the ball was thrown, and what does the range represent? It represents the height, okay? So again, referring back to, our exponent rules and that kind of stuff. So with this here, that goes back to f of x, where this is our domain and f is our range. Okay, so if we input time, we can get out the height, or if we have the height, we can figure out the time. All right, so with the questions here, it says at what height does the ball get thrown, and after how many seconds does the ball hit the ground? So if if you go into GeoGebra or if you go into your graphing calculator, you can use either one. So I've graphed our function here, and it's a pretty long one, and you can kind of play around with the axes here. Look, you can make them big or small. You can shorten this length here, so we can kind of see that arc. So my axes is very different, right? These are the bottoms, are the x values are going by ones. Think about it. You're talking about time in seconds when a ball's thrown. So if you throw a ball in the air, it's not really going to take that much time to come back down, right? You're throwing it up. It's going to come down. That's why it's making this arc on here, right? Throwing the ball up if we're talking about a baseball. Okay. So basically, when you have the ball, there's no time that's passing by. So you're starting at time is 0. So this is our start. And then, we can figure out if this is a max or a min. This is a max height. And you're following along, you don't have to draw this. But you should be graphing it with me using your calculator, using GeoGebra. And then this is where the ball the ball drops, right? It stops, it's on the ground. So basically, when no time has gone by, I just want to click on something. No. Okay, so obviously my measurements are going to get messed up here when I move the screen, but I wanted to show you all the things here. So we have, our two roots are where across the x-axis when y is equal to 0, remember. So we have our two roots. We have one is negative 0.06 and one is 6.06. So the first question on that document was, at what height does the ball get thrown? So we have to figure out, all right, well, if the ball's being thrown, that means wherever the time is equal to 0. So if I zoom in and figure out, all right, well, when time is 0 and x is 0, what's the height? What's y? It's 0, 6. That's also our y-intercept. It's our initial point, our starting point. Okay, so here we have, and I'm just going to erase this so we have more room here. So here is my starting point of 0, 6, right? So time is no seconds gone by, right? I have the ball, but the height at which the ball is already at is at 6 feet. So maybe he's holding it above his head. Maybe he's 6 feet tall. So this is where the ball is starting. So then the ball is thrown and it goes on this little arc here. And we have this max height, or called our extrema. So after 3 seconds, so at 3 seconds go by, that ball is at 150 feet in the air, or its height is at 350. So it tells me this. And then if I go down, the ball's dropping. So where does it land? Or in other words, how many seconds does the ball, after how many seconds does the ball hit the ground? We said 6.06. So remember, the ball's hitting the ground when that height is 0 again. So when that y is 0, y value is 0, the time that's gone by is 6.06 seconds. And that's how long it takes for it to go back to the ground, or it's when it's dropped. Okay, so looking at the roots basically tells you a lot of things. Looking at the max or the min tells you a lot of things about the relationship. You just got to figure out what variables you have. So we had seconds and feet, and be able to interpret that information. On GeoGebra, you can hit this little semicolon and play with these things. So we have a table of values. Maybe you want to plug something in or find a specific value. We have special points. If you click on special points, it actually tells you the roots are right here, and it says root, which is cool. It tells you the extrema, which is our max, which was 350, and it tells me the intersection of the y-axis, or my starting point, which was that 0, 6 value. So this really does tell you so much about this quadratic. Okay. We answered what's the max height, and again on your calculator you can see we've talked about how to find max min. If you go on your graphing calculator, so let's say you don't want to use GeoGebra, you want to use your calculator, you can hit the second button and then hit trace or calc, whatever you see on your calculator, it's up top, and you'll see this list of, you have value, You have 0. So if you want to ever find the zeros, you can click this and play with the bounds. If you want to find the minimum, remember it's here. If you want to find, you hit 3. If you want to find the maximum, you hit 4, and etc. So that's second trace, and you can also find these values using that function, okay? In case you don't want to use GeoGebra. Obviously, you wouldn't have GeoGebra if you were taking the regions, but I'm showing you GeoGebra since you're not taking the regions, okay? All right, so let's keep going. So we answered that question, and you don't have to graph it, but when you do for your independent problem, you're just going to take a picture of either your graphing calculator or GeoGebra, but this is just a nice graph of it zoomed in. Okay. The second one, we're looking at a different function, x squared minus 6x plus 5, and they want to identify the key features. So, graphed, again, possibly how to play with the axes, making it look nice. Really, this is a nice quadratic. I could see what the roots are, right, across the x-axis at 0, 1. Wish I could click on it. I don't know why it's not working, but if I want to see special points, not 0, 1, 1, 0 is the root. 5, 0 is also a root where it crosses the x-axis, the two solutions. This has a minimum of 3, -4, and it crosses the y-axis at nice 0, 5, the y-intercept. Okay, so that's a little exploration. You can take notes on the parts of this graph. You can literally list what I just said here, the roots, the max, the min, and the y-intercept, just so I know that you are watching and you understand those 4 parts of the quadratic. So that was a nice problem to do together. And the last one we'll do together, I'll read through it. So Paige wants to start a summer lawn mowing business. Something you guys can definitely do. She comes up with the following profit function that relates the total profit to the rate she charges for a lawn mowing job. Okay, that's a negative x squared also. You should know that because it's also making that N shape, not U shape. Both her profit and her rate are measured in dollars. Graph the function in order to answer the following questions. So we have so again, this is a little bit harder because they're both talking about money. So one part of dollars or money is the total profit that we have that she's going to get. And the other dollars is the rate she charges. So profit in this case is going to be our Y. And the rate that she's charging is her X. So whatever the rate she charges will determine her profit, which makes sense, right? If you're selling something, you need to figure out at what rate you're selling it at to figure out what your profit's going to be. So right now we got to figure out, like, why is this negative function? Usually when you have a rate and you make money, you should probably be thinking this should be linear. Like, why isn't, if she's just going to keep making money, isn't she, if she does this rate? But think about it. If you keep charging, you want to make sure you have a perfect rate. You don't want it too high or too low. And if you think about it, why is that a question you should be thinking about if you're ever going to sell something or ever going to make money off something? Why is the rate, like, really important? What if the rate's too high? Are people going to buy anything? Or are you going to make a big profit? If your rate's really high, if she's going to charge a really high rate for her lawn mowing business, do you think she's going to make a lot of profit? Or is it better sometimes to have a lower rate and then make a bigger profit? That's something you need to think of, right? Maybe she's in a neighborhood where they can't afford a large rate. They can't afford, $40 for a lawn. Maybe that neighborhood rather $20 a lawn. So this is where you have to think, well, if I charge $20 per lawn, maybe I'll make more money because more houses, more families will want to hire me. But if I charge $50 or $60 per lawn, I may not make that much profit, right? Maybe some families don't want to pay me that much money to mow their lawn. So this is where that quadratic, that U shape or that N shape is coming in, because the rate's not always high. Sometimes you don't want a high rate because people aren't going to buy it. That's why, food places always have discounts and stuff because they can't keep raising their prices because people won't go to their restaurants. So that's just an explanation of why this is a quadratic relationship. But I have this graph here, and I did zoom in and like played with it. So I think it really like looked like this at the beginning, but I kind of played with the axes. I extended it. I'm using my fingers. You can also zoom. There's zoom buttons on the right side. This is full screen. I don't want full screen. You can also play with this thing. Zoom to fit could work as well. So here's a nice picture of my quadratic. I can see where the roots are crossing, and I can click on them. I can see where the max is, and I can see where it's crossing the y-axis. So those are the 4 points I always want to look for when I have a quadratic. Whenever you graph a quadratic, you want to make sure you can see those 4 points. They're very special points. They will help you solve, okay? So if we go back to the questions here. Okay, it's asking, according to the function, what's her initial cost? Remember, initial means like the starting point. Like, where is she starting? The starting point's where it's the y-axis. So if I go to my graph, she's starting at negative 100. What does that mean? She's starting at negative $100? She's what? She's in debt. She doesn't have this money. She doesn't have profit. She spent the money, so she's really got to make some money to like gain this back, right? Why do you think it's a negative profit? Let's think about that. Well, she's starting a lawn mowing company. Maybe she what? Maybe she had to buy a lawnmower. Maybe she had to buy the grass bags to put all the grass in, right? If you've ever seen someone mow a lawn, they have to empty that whole lawnmower can't hold like every grass piece in the world. You have to eventually empty it out. So it's probably why she's in debt. And that makes sense. Whenever you start a company or start something up, you've got to put money in to get money out. All right. So she's in debt of negative 100. That's our starting. Between what two prices does she have to charge to make a profit? So if we look at our graph, we're talking about between what two prices, what two rates can she charge at to make a profit? So we've calculated this as she can start at $2.68 or she can go up to about $37.32, right? We're talking about money, so we can do the hundreds place. What happens if she goes over that? What if she wants to charge 45? Is that a probable value? If we go over to this 45 on our graph, is that even part of our graph? Will she make a profit from that? No, so that might be not like that price might be too high. She's not going to make money off of that. That's not where this equation's showing us a good representation of what she should be doing. So they're telling us she could charge between $2.68 and $35.32. Obviously, she's probably not going to go that low with the $2. That's insane to be mowing a lawn for like $2.30 unless we were like in the 1800s. So if I were her, I'd probably be between like, 25 and 35. I'd probably go my highest, depending on the neighborhood, depending on the lawn. If maybe it's a really small lawn, so you do $10. Maybe it's like your grandma, so you charge her less, or maybe she'll just give you more because it's your grandma. I don't know. But those are the two zeros, so they tell us the interval of, what prices she can charge to make a profit. And again, if you're using your graphing calculator, you can hit second calc and calculate the zeros. If she wants to make a $270 profit for the summer, is this a right business choice? Yes, there are profits of up to 300. Remember, 300 was our other special point. It's our maximum. So that's like the highest she'll make from charging between these intervals in this amount of for this rate. So yeah, she'll be able to make $300 if she does this. And so she'll definitely make 275. So it's within our range. If we said, can she make 500? No, she's not gonna be able to make 500. We'd have to change the equation. We'd have to change her rate. We might have to change just whatever she's doing to be able to make that. All right. So hopefully that helps you. You're gonna you're going to copy the notes that we just kind of went over as best you can. I'm not going to be picky. You don't have to draw graphs, but hopefully you played around with GeoGebra or your graphing calculator. You can label the questions as page, label them as best you can. I kind of just want to see the special points of these graphs. And then I really want to see you doing this on your own. A student throws a bag of chips to her friend. Unfortunately, her friend does not catch the chips and the bag hits the ground. So, think about someone's tossing you a bag chip, right? Distance from the ground, so height for the bag of chips is modeled by the function, where h of t is the height and t is the number of seconds the chips are in the air. So they're telling you what the domain and range is. It says graph. So again, I want you to either take a picture of your graphing calculator or take a picture of GeoGebra, whatever model representation you're using. You're not going to do it on paper. That's silly. We have technology right now. B, from what height are the chips being thrown? Tell how you know. So again, you should be looking for special points for these questions. You should be looking for the roots, the y-intercept, and the max or min, depending on the quadratic, to help you figure these questions out. Do your best. What is the max height of the chips? How many seconds after the bag was thrown did the chips hit the ground? E says, what is the average rate of change? Think about average rate of change. Google it if you don't remember. You should be thinking of like a slope, possibly. And we've had that on certain tests, so hopefully you remember. If not, look it up. What is that? And if you still have a question, email me and I'll post something about it if you don't remember. And see if you can answer letter F. Okay, if you do have questions, email me. Use your resources, use GeoGebra, use your graphing calculator, but I'll explain what you need to submit again if you didn't get it from the video on the assignment.